Welcome to Veteach. So till now we have discussed various architectural styles for cloud computing applications till the previous video. So we'll start a discussion for the workflows. So workflows, and then we'll proceed discussing regarding the zookeeper, how to coordinate the workflows. So then we'll proceed with the map reduce model and conclude. So workflow represents, so the process description. So it is the structure describing the tasks to be executed and the order of their execution. So generally a workflow represents the sequence of activities that are to be carried out, similar to a flow chart. So it is a structure describing the task to be executed and the order of their execution. So the other term case, so an instance of the process description represents the case, and the state of the case at any time t is defined in terms of tasks that are already completed at that time. So at that state, so when we talk about state of a case, that is how many tasks are completed at that corresponding time, that is represented as state of the case. So we will see the similarity between the workflow and the program. So if you observe, so dynamic workflows, static workflows, two types of workflows, dynamic and static workflows. These are represented with workflow description language. So as in the programming language, the static programs are represented by way of programming languages. Who writes? So this user. So component database will have a planning engine which describes the workflows. The programs are described by computer program from which uses the component libraries and sometimes the automatic programming part for dynamic programs. For dynamic workflows come from the component databases, and the planning engine generates the dynamic workflows in the form of workflow description. So these workflows are verified in the verifying engine, whereas the programs are verified in the verified by the compiler. Then after that, these workflow descriptions are put in the workflow database. Here the programs are converted to object codes and put it in the program library. The enactment engine is the one that compiles the workflows and store, and by way of case activation records, so these will be stored. So by the data that is given as input for processor to run the applications. So runtime program modification requests, those are sent back to the dynamic programs by way of automatic programming. Here unanticipated exceptions, if there are any errors, those will be traced back to the planning engine. So this is how a workflow coordinates the activities, or is coordinated by sequence of activities as programs in our general scenarios. So workflows to be categorized as static and dynamic. Static workflows are written in workflow description language. Dynamic workflows are generated by planning engine from the components of present in the component database, which are put to the verification engine, then forwarded to workflow description, which are stored in the workflow database. So data which is received from by way of case activation record. Any unanticipated exceptions, those will be traced back or moved back. So two important characteristics of a workflow are safety and liveliness. These are the two desirable properties of any workflow. So safety, the workflow should ensure that nothing bad happens in the sequence. So liveness, it should show that something good will eventually happen. So safety should ensure that nothing bad ever happens. Liveness should ensure that something good will eventually happen. So this is one representation where it violates the liveness requirement. So this particular scenario here violates the liveness requirement here. So A, so when we after it goes to B, it goes to either D or C. So when it goes to D, it is eventually missing out the F part. So where it violates the liveness requirement here. So the other case here, task A and task B are found to be mutually exclusive. So task A and task B need exclusive access to two resources R and Q. So here there is a possibility of deadlock to occur if the following sequence of events occur. So at time t1 A acquires R, time t2 B acquires Q, and this continues to run. At times t3 task B attempts to acquire R and it blocks because R is under the control of A. So task A continues to run and T4 attempts to acquire Q and it blocks because Q is under the control of B. So in this case there is a possibility of deadlock where this is not expected. These are violating the liveness requirement. So what is this liveness? So something good will eventually happen. So in this scenario, good is eventually happening but not regular, and there is possibility of getting fail. So we'll see the basic workflow patterns. So these represent the temporal relationship among the tasks of a process. So if A, B, C, D are number of tasks, the relationship between these tasks are represented by way of the workflow patterns. First being the sequence. Several tasks have to be scheduled one after the completion of another. So A, B, C, these are to be scheduled one after the other. And split. Second workflow pattern, and split. Both tasks B and C are activated when A is terminated. After the completion of A, B and C gets started at a time. Then synchronization. Task C can only start after the task A and B terminated. A, B, when both of these tasks get closed only, task C can start. XOR split. After the completion of task A, either B or C can be activated. So after this, there is a possibility of B or C to get activated. Either of these two will get activated after this A. We will see the representations in the next slide. Then XOR merge. Task C is enabled when either A or B terminated. So we might be having A or B. When either of these two get terminated, C gets activated. XOR split. After the completion of A, one could activate either B, C or both. So if we have A here, B, C, after the completion of A, so either B or C could get activated, or sometimes both of these might be activated. Then multiple merge. Once task A is terminated, B and C execute concurrently or parallelly. So once A gets stopped, B and C will execute parallelly. When the first of them, say B, terminates it, then T gets activated. When this is terminated, D gets activated. When C gets terminated, D gets activated again. The other one, discriminator. So this waits for the incoming branches to complete. So when a number of incoming branches, when they come, waits for number of incoming branches to complete before activating the subsequent activity. So this waits here until all the incoming activities gets completed. Then wait for the remaining branches to finish without taking any action until all of them have terminated. Next, it resets itself. Then a node of M join. So this is the barrier synchronization. For suppose we have M tasks run concurrently in parallel. When we have M tasks that are running in parallel and N of them, some of them have to reach the barrier before the next task is enabled. So for suppose we have 5 tasks, assuming that we have 3 tasks have to be reached the barrier before the next task is enabled, that could be considered. So the example that we show, any 2 out of the 3 tasks ABC have to finish before E is enabled. Deferred choice. This is similar to XOR split, but the choice is not made explicitly. The runtime environment decides what branch to take. See here. So first one, sequence A, B, C are being carried out sequentially one after the other. And then A after A, B and C will take into picture. Second one, and split. Both tasks B and C are activated when A is terminated. Third one, A and B. After A and B get terminated, C gets activated. A XOR B, C. See here, D XOR split. After the completion of A, either B or C can be activated. After the completion of A, either B or C gets activated. Either. When either of A or B gets activated, terminated, C gets activated. When either A or B gets terminated, C gets activated. And then A, when this gets terminated, B or C will get activated. B or C gets activated. And then G, X or split. After the completion of A, one could activate either B, C or both. After the completion of A, either B or C would activate or both, and after that it goes to B. And then A, so either B and C will get activated, discriminate to D. Now here in this example, discriminator, n out of m join A gets terminated where B, C and D are have taken their choice, and out of which 2 have to be completed, 2 by 3. Out of which 2 have to be completed, 2 or 3 that is listed out here, then E gets activated. Then E gets activated. And then the last one, A XOR B or C. Deferred choice. Similar to XOR, but the choice is not made explicitly. The runtime environment decides what branch to take. So, after the completion of A, the runtime environment, the program decides which one to get activated, B or C. So, these are various workflow patterns. So, this is the thing, workflows. So, coordination of various multiple activities is taken by the workflow patterns. Thank you.